welcome to Calculus. We are going to study the trapezoidal rule today, and what it boils down to is the trapezoidal rule is just another way to find an approximation for area under a curve. We've studied so far rectangular approximation methods like LRAM, MRAM, and RRAM. And the trapezoidal rule just gives us yet another way to study the area under the curve and find approximations, etc. It turns out on the AP test there are almost always, going to be trapezoidal rule problems on there, so it's very important that we are able to find approximations using this particular rule. What it boils down to in simple terms is that if we take the LRAM approximation and the RRAM approximation and we average those two, we get the trapezoidal approximation. Alright, and then the next part, if you take a look at the following formula I have from your book, which is on page 290, we have the trapezoidal rule here, and as you can see, the trapezoidal approximation to approximate the area under the curve f of x from a to b is h over 2, and h, of course, here is the interval length b minus a divided by n, which is the number of subintervals. And then the information in the parentheses here are the y values at each of the points in question in terms of how we've done the subintervals. So this would be the left endpoint, y0, then the next y value to the right, and so on until we get to finally the right endpoint. And notice with LRAM and RRAM, we only use either the left endpoint or the right endpoint, not both, whereas the trapezoidal rule, we use both the left endpoint and the right endpoint, and each of the intermediate y values are multiplied by 2. And ultimately what this formula does for us is it calculates the trapezoidal shapes that could be created by using the points from the y values in the subinterval. So bottom line is there's one important part to this particular rule that you have here in your book, and that's that this can only be used when you have uniform subintervals. So the formula, again, h over 2 times y sub 0 plus 2y1 plus 2y2 and so on up to 2y n minus 1, 2y sub n. So again, that formula is to be used only when we have uniform subintervals. We will discuss non-uniform subintervals soon. So, for argument's sake, if we wanted to take a function, one that we've been dealing with, say we go from 1 to 3 of x squared dx, and we wanted the trapezoidal approximation for that with, let's say, 4 subintervals. So notice the subinterval, the length of the interval is 1 through 1 to 3, so the length is 2, of course. So 4 subintervals. Picture-wise, just so we can be clear on what the picture would look like if we were to do from 1, 2, 3, and we draw our graph as such, and ultimately the trapezoidal approximation would be like this. The drawing part of it would be, we would just essentially take the two y values in question and we'd connect the dots. And these two shapes would be if we had 2 subintervals. If we wanted to create 4 subintervals, then we would change it to having 4 uniform subintervals, and we would connect the endpoints as such. And again, just like LRAM and RRAM, we could individually just find the areas of each of those trapezoids. But if we did so, again, that would be an option, but we also have formula that we can use too that we see above. So with that said, if we figure out what our h is, keeping in mind that h is equal to b minus a over n, which for us b minus a would be 3 minus 1, subintervals would be 4, so ultimately our h value here would be a half, and keeping in mind that the formula states that we need h over 2, so therefore the number out in front of our parentheses we write is going to be a quarter, because we have a half over 2. So we'll put a quarter in front, and to fill in our blanks here we need the y values. The y value at the left endpoint is going to be 1 into the function, which would be 1 squared, which is 1. The second point here is 1 1/2 or 3 halves. If we square that, we get 9/4. However, each of the intermediate ones besides the left endpoint and the right endpoint need to be multiplied by 2 as shown in the formula. The next one, of course, is going to be 2, and so if we put a 2 in there, we get 4, so 2 times 4. And then the next one we put in there is going to be 2 1/2, 5 halves, and that squared, of course, is 25/4. And then finally, the right endpoint here, which is 3, if we put that in there, we get 9. So all told, if we want to get the trapezoidal approximation for said function, then we will take calculator or not, depending on how difficult the calculation is, and do the math, if you will. So in the second part, we got 18/4 and 8 and 50/4 and 9, and we ultimately get 8.75. Now, just as a check, we also know that if we use our integral command in the calculator, we can get a check to see what the approximation for the actual answer is instead of the approximation. And so if we use our integral command, we type in our function, and we punch that out. Looks like it's 8 2/3 if we were to make it a fraction. So our 8.75 is fairly close. Obviously, it would be better if we had more subintervals. And one thing to note too is in terms of overestimate or underestimate, we do have an overestimate here, and ultimately the reason for that is that the fact that the function here is it has to do with concavity when we deal with the trapezoidal rule, and we can see that this particular function x squared is concave up, and therefore on that interval, if it's concave up, we're going to get a over approximation, if you will, an overestimate. If this had been a concave down function, it would have been the opposite. So, moving along, if we take a look here at another type of trapezoidal rule problem where we don't necessarily have a function given as an equation like we did in this one. If we have one like in your book here on page 291, we have the function given as a table, and we have some times and temperatures here, and ultimately the question here asks us to find the average temperature over the 12-hour period. Keeping in mind that when we have an average temperature and we have a temperature function, if we're looking for the average value of the function, then we're going to be using our average value formula that we have from our previous sections. And so essentially, of course, the 1 over b minus a is easy enough, and 1 over 12, if you will, is our 1 over b minus a part, because we're looking at a 12-hour period here in this problem. If we want to approximate the area under the curve, of course, we don't have enough of x that we can actually find an antiderivative for, etc. So we have no choice but to approximate it using, again, we could use LRAM, RRAM, or MRAM. However, if we use the trapezoidal rule, that's yet another option. So in filling in the blanks here, as you can see, we have h over 2, h being the interval length 12 divided by the number of subintervals, which is 12. So h, of course, is 1. And then as we look at what they've done here, which is exactly what we would do in a given problem just like this, is we would take our endpoints, our y values, if you will, for temperature, and we'd plug them into the formula appropriately, and we'd do the math. And bottom line is we get 782, but again, keep in mind that that is essentially a total, and we don't want 782 as clearly not the average temperature over this 12-hour period, but remember we're doing the average value. This total is just the area under the curve, and of course we know that we need to do one final step, which is multiply by 1/12, which is our 1 over b minus a, and therefore we get 65.17. So bottom line is we use the formula in exactly the same way, but we need to just follow the formula as such, and if we do so, it's fairly easy to apply. And again, keep in mind that this is only going to work if we have uniform subintervals. Otherwise, this formula that we see here is not going to work. So, all right. The next type of approximation that we have here is what we call Simpson's rule. And with Simpson's rule, as you can see on your page 292, it's very similar to the trapezoidal rule, except for the h is divided by 3. And you can see that alternately we multiply the y values by 4, 2, 4, and so on until we get to the right endpoint from the left. Keeping in mind that Simpson's rule is only going to be useful to us if we have an even number of subintervals. Because ultimately what it boils down to is the first y value that is right of the left endpoint, if you will, has to be multiplied by 4, and then the subinterval immediately to the left of the right endpoint has to be multiplied by 4 also. That would not happen if we had an odd number of subintervals. So bottom line is if we have an even number of subintervals, then we can use Simpson's rule. And what it boils down to is Simpson's rule gives us a little bit better approximation because instead of having a trapezoid shape, the shape of the top that connects the endpoints is parabolic in nature, which means that it's going to be a little bit closer to what the actual curve looks like, which is nice, and we'll get a little better approximation. Right? So bottom line is applying Simpson's rule is going to be very much like you did for the trapezoidal rule. You can see for the function in example 3 they gave you, you can follow that fairly easily based on what we've done with the trapezoidal rule, so I'll leave that to you. The next part that I wanted to talk about is the AP type problems that have non-uniform subintervals. So let's take a look at that. An approximation might be something like this, where a typical problem would be where we'd have a table where we have an x and y, whatever the x and y stand for really doesn't matter, but bottom line is say we have x be our time, and say we got time 0, time 5, time 7, and time 14. So ultimately we can see that we have a non-uniform subinterval, and let's say that the values here, let's say we go 0, 1, 5, 4, 7, 8, and then we'll go 14, we'll go back down to 5. So ultimately the question is going to be, can we give a trapezoidal approximation for the area under the curve for the function that contains these points, if you will. So bottom line is if we need to do that, we can't use our formula because the h and whatnot would not be relevant here because the subintervals are not uniform. So therefore, if we plotted our points, we got 0, 1, we have 5, 4, we have 7, 8, and then we have 14. We're back down to 5 here. We're bar here. So we're a little bit too far to the left, but bottom line is that would be our curve. And so whatever the curve looks like in between these, this is all we have to go by. So it has some general shape. Again, just say for argument's sake that it has this smooth shape like that. And the question though is, again, can we estimate the area under the curve using the trapezoidal approximation? Well, like I said, bottom line is since it's non-uniform subintervals, then we cannot use the formula. So what we need to do is just go ahead and connect these points that we just created and create our own trapezoids. And then what we're going to do is just individually find the areas of each of those individual trapezoids. Okay, and so those 3 trapezoids would look as such. So knowing that, and knowing that the formula for a trapezoid that we learned in geometry was 1/2 times height times base 1 plus base 2, ultimately the average of the bases times the height, then we would go ahead and calculate here, and in this particular one we'd have a height of 5, as we can see, from 0 to 5, and the heights here of course are going to be your bases. So we have a height of 1 and we have a height of 4, so we'd go 1 and 4, and ultimately that would be 12 and a half. So we got 5 times 5 times a half, and then the second one we have a length of 2, this being the height again. The heights of or the bases, if you will, which are the heights in this graph, are 4 and 8, so we'd go 4 plus 8, and ultimately we'd get 12 times 2, that's 24, times a half would be 12. And then for the last one, we would have a length of 7 on the bottom of it, which is the height of the trapezoid. And then the 2 heights in question here are 8 and 5, so we'd go 8 plus 5. And then from there, we could add these together, we'd get 13. And 13 times 7 is 91, and so we get 46 and a half here. Okay. And ultimately, we would add those all together. And if we did that, we'd get 24 and a half plus 46 and a half would be 71. And that would be our approximation for the area under that curve based on these points that, again, come from a non-uniform subinterval. Just to illustrate a point that I mentioned earlier here, if we, when I drew this, I drew it concave up here, notice that that particular trapezoid gave me an overestimate for that part. And then on this part, it was concave down, and notice that when we drew the trapezoid here, we got an underestimate. As I mentioned earlier, it has to do with concavity. The concave up, we're going to get an overestimate. Concave down, we're going to get an underestimate. And if there's if there's a change in concavity, obviously, then it depends on how concave they are and what length the intervals are and so on. Okay, to conclude our lesson for today, I want you to take a look at page 294 of your book. Here we have the what we call error bounds. And bottom line is, of course, there's error here when we use trapezoids to approximate real areas under curves. And what it boils down to is if we use the trapezoid rule and the Simpson's rule, there's an error bound that we can calculate, and ultimately the error bound is going to be the most error we could possibly have with using one of these two rules. And you notice that the error bound for the trapezoidal rule is fairly simple to calculate. We just need to have the interval length over 12, and we multiply it by h squared. Of course, h is still the same h we used in the previous part. And then this notation is the different part for us today, and that's the m of f double prime. And what that stands for is the maximum value of the second derivative. So ultimately, whatever the function that we have, whatever that function is, if we find the maximum value of the second derivative, then we ultimately will be able to calculate the error bound. And again, we're going to find an answer here that's going to tell us, okay, how far off from the actual answer is this trapezoidal approximation? How far could it possibly be off? And the same thing with Simpson's rule. We just do the same thing, except for it's 180 on the bottom. We have h to the fourth here, and this time we want the maximum value of the fourth derivative. And so if we can calculate those things, then we can get this number, and ultimately that number is how far off the Simpson's rule can possibly be. So looking back at the one that I did earlier here, remember a few minutes ago we got 8.75 for our trapezoidal approximation. We got 8 2/3 for our actual answer here. And we can see that between 2/3 and 3/4 there's some error there. And what it boils down to is if we calculate the error bound for this particular function, then we would have found that the error is going to be something probably a little bit more than how far apart these are, because ultimately there's error here, and the error can be no more than this. So that is the bottom line here for working with the trapezoidal rule and Simpson's rule. We do have calculator programs for both of these, for trapezoidal rule and Simpson's rule, that we'll be using as well, and we will use those at a different time. So that will do it.